Hey everyone, thank you all for joining for another awesome Apache Pinot meetup. So today our topic is optimizing Apache Pinot's query performance. We have two presenters today. We have Subbu Subramaniam, sorry, I butchered that, Subramaniam, and Jackie Jiang. So Subbu's going to go first. We're going to have him come out. His topic is optimizing Pinot's real-time performance. Following his presentation, we'll do a Q&A, and then we'll send him backstage for a little bit. We'll have Jackie come out. Jackie's going to do a couple talks, optimizing query performance, of which index to use, and also filter optimizing and segment pruning. So those are the two topics, or those are the two speakers for today. So if you have any questions, please ask in the chat right here in the YouTube chat. If you are watching this after the live stream and you do have questions for the speakers, feel free to join the Apache Pinot Slack and you can ask them there. Subbu and Jackie are both very active in the Apache Pinot Slack. So I'm just going to give a quick summary on our presenter today. So Subbu has been working on Pinot for the past 5 years, and he has designed and implemented much of the real-time infrastructure in Pinot, right? Crazy. Prior to joining the Pinot team, Subbu worked on a variety of technologies using key value stores, Espresso at LinkedIn, Peanuts at Yahoo, and then change capture technology, Databus at LinkedIn. Subbu has experience working on embedded systems as well, building redundance and fault tolerance in network switches. Pretty awesome background. So I'm going to welcome Subbu. Hi, Subbu.
Hey, Karine. Thanks for a nice introduction there.
Yeah, it's awesome. I'm really excited about this. I think a lot of people are going to be really excited about this topic. So, I'll hand it off to you. Afterwards, we'll come back. We'll do a Q&A. Just for those watching, sometimes there is a slight delay. So if you do have questions for Subbu ahead of time, feel free to ask them in advance, and then we'll ask them during the Q&A. So it's okay to fill up the chat, and we'll just ask them once he's done his presentation. All right, Subbu, thank you. I'll let you take it away.
Cool. Thanks much, Karine, and welcome everybody. Good morning. Just so you know, I'm missing a talk by Leslie Lamport at LinkedIn in order for me to give this presentation. So you guys are obviously more valuable than Leslie Lamport. All jokes aside, so I hope you have a good time here listening to real-time performance of Apache Pinot and how we can make it better, and what the futures are and so on. But before I start off, an acknowledgement to all my colleagues who have contributed towards building this knowledge, both past and present. Okay, so we'll go through an overview of Pinot, and then some factors that influence performance of real-time Pinot, and then how we can tune Pinot to get these factors under control, and then some future ideas that I have on performance improvement. So starting with the overview, many of you may already know this, but nevertheless, it's good to start off with something like this. So Pinot has multiple components that we work with, controllers, brokers, offline and real-time servers, and Helix is our cluster manager framework, which uses Zookeeper as the metadata for data for Helix and then metadata for Pinot. And we have a segment store in which all the Pinot data is stored as permanent store. The segment store can be populated via batch data push, which goes to the controllers, and the controller stores it in the segment store. And an alternative way is to just push directly data to the segment store and then let the controller know the location of the data. And then the controller takes care of that from there. And one of the first things that happens is when an offline blue segment is pushed, basically the offline servers get notified that they need to host the data, and they start pulling down the data from segment store, and they host that data there. Similarly, on the real-time stream, there is a real-time inbound stream that comes in, Kafka, and now we have other streams as well. And the servers start consuming them once the table is created. Every once in a while, the server does a periodic commit of the real-time segments, And they are also stored in the real-time servers for serving purpose. And once that is there, the segments are in the deep store real-time as well as offline segments. The queries come straight to the broker. The broker federates them across the real-time and offline servers, gets their response, and passes the response back to the user. So on the real-time front, zooming in a little bit, the architecture is as follows. So you have partitioned stream like Kafka or other streams. So imagine you have P1 through Pn, n partitions of stream with each of those boxes representing messages, and you have multiple servers consuming those partitions. In the consumers, you have a Pinot indexer and a query server. The indexer and the query server are common, but there is a partition consumer that is instantiated, one per partition consumed on the server. So if a single server consumes 8 partitions, then you have 8 instances of the partition consumer in the servers. And of course, each partition can be consumed multiple times for redundancy, and we don't place redundant partitions consuming on the same server. So we have different servers so that in case one goes down, you have somebody else consuming and indexing that partition for queries. So this is the layout of real-time architecture of the service. And in this case, the queries are routed to cover all partitions and all segments of all partitions in the past and present. Okay, so we have what's called a Lambda architecture, which is basically, imagine this is your time progression, and you have real-time data that has been consumed for August the 2nd, 3rd, 4th, 5th, and 6th is being consumed right now. And imagine you have offline data that has been pushed from Hadoop or some offline system for 2 years until ending August 3rd, let us say. Let's say you have a 2-year retention on the table. So all the old data is available on the offline part of your table, and all the new data is available on the real-time part of your table. And you as a user see only one table. So how do we do this? So we have, let's say a query comes in, select sum of metric from the table. And if you send it to both offline and real-time, then you're going to get duplicate data for the 2nd and 3rd of August, right? So we avoid this by keeping what we call a time boundary on the broker. And the broker maintains that time boundary. As new data gets pushed on offline, the time boundary keeps shifting. So for offline, so now the time boundary is between 2nd and 3rd. And so then the broker, when it gets a query like that, it basically sends an offline query to the offline servers, something like select some metric from table where date is less than August the 2nd. So it adds the where clause, and it adds another where clause to the real-time table, sending a different kind of query to the real-time servers. And then it gets back the two and can consolidate and return the results to the user. Zooming one level further on real-time segments, let's say you have partition 4 being consumed on a real-time server. And the last one here is the currently being consumed, the one being consumed. So that's the current time. And these are the completed segments. Like I said, there is a periodic segment completion. And somewhere here is our time boundary or other query boundary. I mean, you might have real-time only tables in which you don't have time boundaries, but you probably have a boundary of queries saying most of my queries are going to be between this and time and current. Maybe it's the last 1 day. 90% of the queries are going to be in the last 1 day or something like that. So that would be your segments. And then there would be some segments beyond that subject to the retention of your table. You might choose to retain your table for 30 days. Most of your queries would be for the last 2 days maybe. And some of your queries may span 30 days. So you want a retention of 30 days, right? That's very possible. So we have 3 types of segments there. You have the completed segments, which are dark green and probably cold, rare reads. And what I call the completed segments warm, which is read-only. It's not read-write material. And then the consuming segments, which is being written to. So the consuming segment is continuously getting rows from underneath from the streaming layer, and it's indexing them as they are ingested and makes them available for queries. There may be another partition being consumed. In fact, several partitions being consumed. In this case, partition 7 is being consumed, and they are the segments there. And if you notice, on purpose, I have drawn the segment sizes to be slightly different from each other. They're not guaranteed to be same size. They try to adjust to the size that you specify. So they may go over a little bit, they may go under, depending on the ingestion rate that's coming in. And so they learn as they go. And so it could be slightly different. And the time boundary could be well, in the middle of a segment, or the query boundary for that matter. Okay, so the learning from here is that all the segments that are, the important point to note here is that all the segments that are loaded as memory mapped file. There are some exceptions here, and we'll walk through those exceptions a little bit later. But this is an important point to note, that they are a file on disk, the segments, especially the last one, the consuming, the non-consuming ones, the completed ones, files on disk, and they are just mapped in memory. Okay, factors influencing performance. What are the questions? What do we mean by performance of real time, right? I think there are two questions that are important here. The first one is, are rows showing up late in Pinot? If so, then something needs to be done. The second one is, are queries not meeting the SLA? I wouldn't say queries are slow, because slow or fast depends on what your SLA is. If you have a 10 millisecond SLA, then 12 milliseconds is slow. If you have a 500 millisecond SLA, 12 milliseconds is awesome fast. So these are the two main questions that basically the real-time system has to deal with. And if these two questions are basically coming back with, oh, everything is good, then you can probably go get a bagel and coffee and probably skip the rest of the talk, or just use it for entertainment. A related question here is, can we keep it going with less hardware? So you might want to think about that, right? So with these three questions, let us see what factors influence the performance of real-time systems in particular. And I'll specifically talk about real-time. I know there are other things as well with Pinot performance, but this one's talk is concentrated on real-time. Okay, so what are the factors involved? There is ingestion rate. The higher messages ingestion rate, the more work the real-time server has to do in indexing and indexing the messages. So that's going to take up some CPU, and that can cause either slowness on ingestion or slowness in queries, depending on how things are, how much is left over, juice is left over on the machine. There's a schema width. You can ingest at 50,000 messages a second per partition if you have, 3 columns or 5 columns. If you have 5,000 columns, you probably cannot do at that rate. It will take time to ingest the row. And only after the entire row is ingested is it made available for queries. And the schema width is both number of bytes per second as well as a number of fields. You might have small number of fields, but very large width fields. Or you might have a large number of fields, but multiple of them small width. Either way, the schema width is going to play a role. The number of partitions in the stream is going to be there, going to be an important factor. If you have 2 partitions versus 20 versus 200, you will need appropriately the setup to handle that many partitions. The type of indexes used for each column. You might use inverted index for some columns. You might use no raw index for some columns, and so on. And that translates to, that's a factor involved. The time boundary or other limit, the other line that limits the warm segments. So if you choose to have 100% of your queries go over 30 days versus 99% of them go over 2 days, it'll make a difference. You could optimize your setup so that you can derive better juice out of your hardware if you know the way your queries are going to get the rows, the days that your queries are going to touch. The segment size is important. Frequency of segment completion. If you're completing a segment every minute, you're going to have a lot of segments. Then you have memory available on the servers. Obviously, more memory is better, like always, but you can optimize it, you can tune it. And then how many servers are you going to be using for the table? If you have n partitions, and if you have, for example, 2 replicas, you really cannot do more than 2 n servers. Beyond that is useless. So each partition, each replica of a partition can be consumed in one server. But typically, we don't have to go to that lengths in Pinot. And in fact, most of the early use cases are that you just get onto it, you start it, and it works. You can start it with a few hosts, and then you can tune it from there. But there are a few things to understand what goes on. It's useful to understand what goes on behind the back, and then you are better equipped to tune your installation. So one thing is, we don't want too many big segments or too few small segments. Both are not healthy enough for Pinot. If you have a big segment, then that's going to take time. The queries are executed, and Jackie will go over this in a more detail, perhaps in the next presentation. But the queries are executed one segment at a time. So a thread is allocated for a segment, and the entire segment is processed by that thread. So if you have very big segment, then your parallelism is going to reduce. On the other hand, if you have too many small segments, then there is some overhead in terms of scheduling a segment, and then switching it back to a new segment, and so on. So there's going to be overheads there. So you really want a sweet spot, and there is no right number here. We have often toyed with about 200 to 300 meg as a right number. But if you have 5,000 segments that need to be searched with 200 to 300 meg, maybe it's better to make it bigger and search smaller number of segments. Either way, it can be scaled. And Pinot is flexible in that respect. So you can choose these parameters to get to where you want to go. All hot and most warm segments will be in memory or paged in, depending on how your memory is. If you don't have enough memory, then they're going to be paged in. The server will experience paging if active memory is less than available memory. That is, generic truth of nature, but it's good to keep in mind when you're tuning Pinot performance. And that can result in higher query latencies because segments have to be paged in before they can be scanned for queries, or even slower segment completion because the segment build will take longer. The segment completion is another thing to keep in mind. Like I said, periodically there is a segment that the consumption finishes and completes the segment, and then the new consumption starts, and all that happens on a per partition basis. The segments during completion we don't consume at this time. We pause. Typically, segment completion takes tens of seconds. So during that time, the consumption is paused. So you will get not so fresh data for 20 seconds or so, or 30 seconds, depending on the size. Again, a lot of factors determine how long your segment takes to complete. It does
really quick,
increase.
Subbu. Sorry to interrupt. There's a question that came up that's relevant to this, and I wanted to just confirm that this is like the accurate thing. So Ken Krugler asked, did you mean to say too many small segments or too few big segments?
Correct. So yes, too many small segments is not good, and too big segments are not good either. If you've got very large segments, then that's going to take less away from your parallelism. But if you have too many small segments, then you're going to have overhead in switching. So you really want to find a sweet spot of the segment size.
Okay, cool. Thank you for clarifying. I just wanted to make sure. I was like, I'm going to ask this now, just in case people are watching this on demand later.
Okay, sure thing. Of course.
Thank
you. Okay, so yes, thanks for your question, Ken. So segment completion does pause your consumption, and it does increase GC overhead during the completion part. And then after that, you will have less GC perhaps, but there will be some GC while the segment is being built. The server restart causes consuming segments to discard data and restart consumption. We all work in live, those of us who work in live installations, restarts are a way of life. They can happen. either with or without control. Sometimes we want to upgrade servers and we do a rolling upgrade, then we restart servers and we don't, look to see what state the segments are. We don't have that kind of time. So it does cause the consuming segments to discard data and restart consumption. Now, typically that's not a problem, but there are things that you can tune if that causes to become a problem for you. The takeaway here is we need to keep the working set in memory as much as possible, or be tolerant towards its paging, one of the two. A little bit more detail. Most of this probably will not affect most installations, but it's good to know, again, if something pops up, it's good to know what's going on here. How do we allocate memory for consuming segment? So in the consuming segment, the rows get indexed continuously and they have to be available for query. And so one would think of a consuming segment as something that starts like this and keeps growing. So what we do is we actually pre-allocate memory for n rows, and the cardinality, and depending on the cardinality, ki for each column I, right? It's made available it's allocated on a columnar basis. And it's all off heap, which means it is again memory mapped for most parts. There is heap memory used for inverted indices, which is allocated on demand. So that heap memory is basically what your XMX heap that you specify when you start the JVM, and that is sort of unmeasured. We don't know how to measure it. There's a question again from Ken. What's the best way to estimate the working set size? Is it summing the uncompressed segment sizes of all hot warm segments? That would give you one way, but I will give you a tool that can help you estimate that, because it's very hard to do that on a per use case, per table basis. So the value of n is basically decided based on a predicted segment size. So what we do is we choose the segment size. When you configure the table, you can choose a segment size. So say I want 200 meg segments, or I want 500 meg segments. And then we adjust the number of rows so that we try to reach that 500 and stay as close as possible. And the pre-allocation is based on learning from the cardinality from the previous segments. So the previous completed segments will give us some indication of, oh, this value, this is data center ID. It's likely to be 4 or 5 maybe, and this is a link, a user URI or something, which is likely to be infinite, that sort of thing. So we learn from there, and then we get the allocation based on that. And then, of course, if a segment deviates from its previous segment's properties, you do see additional allocation. We try to avoid it, which is why we try to learn from previous segments and add a little bit extra to it. Because if we make additional allocation, that means in query time, we got to chain these and scan through them or walk through them as the query comes in. So for high query performance, that's not very, very good. So we try to not do additional allocation, but it does happen occasionally. The forward index and raw index memory, they're all order of n, and the value store is order of cardinality. So as new values come in, we build a dictionary, and the value are kept in the value store, and then there's a dictionary, which is essentially a hash table of mapping of value to the ID. And that dictionary is also of the order of k, the cardinality, but there is a problem with the dictionary, that the dictionary is actually a hash table. So depending on the kind of values that come in the stream, you might hash at different places, and so you might actually touch different areas of that memory. The idea behind going through this detail is that it is useful to keep in mind that not all consuming memory is just only the first part is touched, or only the first part is read only, and the last part is read write. It's not necessarily the case. There is some part that is read write as well. And I think we all know that if you have read write memory, then you're going to have more dirty pages on your system, and then they have to be written back, and so on. Okay, question from Elon: is there a config to control whether inverted indices are stored off heap? We don't have off heap inverted indices as yet. Good question, and we are looking for contributions in that area. We haven't worked on it for a while, but so far it has not, at least in our installation, it has not uh, worried us too much. Okay, so the takeaways here. Um, Not all consuming segments memory is read-write. A lot of it is actually read-only. Some of it is read-write, but the read-write portions are the ones that are going to be paging more in and out, and you're going to have dirty pages. So it's good to know that it's happening. It's good to look at your system, see what's going on there if you face problems. The dictionary memory is unpredictable for large cardinality, because if you have cardinality of 10,000 and sometimes 8,000 values come in, sometimes 12,000 values come in, then it gets a little harder. Depending on the time of day, if different values are coming in the segment, and we made a previous segment, we think it's 10,000, but now it's 12,000. Reallocation happens in that case, and unfortunately, that is fact of life in large-scale systems. Consuming segments use some long-term heap memory, like Elon just acknowledged that the inverted indices is one. And the segment size and memory allocated stabilize over time. The segment size we learned from the previous one, like I said. So the way we do that is we start off small, and then we increase the number of rows consumed per segment as time passes, and until we reach the segment size, and then we are like moving really slowly. So it does take a few segments completion to get to the right size. And similarly, the memory allocated takes a few segments completion to get to the right size, right? So because of this, if you start a real-time table today and do a performance test, it may not perform as well as you let it consume for a couple of days and then do the performance test. You might get better results. Again, this probably matters if you're doing really high throughput ingestion or very high throughput queries. If your system is working fine, just you're good. It's good to know what's going on in the background, and hence I added this. Okay. All right. So what I've given you so far is all the variables and all the unknowns that are there. And so how do you control? So what we have done is given you some tunables in order to do this. So what are they? There is a software called Realtime Provisioning Helper. It's a Pinot admin command. You can run that command, and it helps you decide the segment size for your parameters, for your set of systems, for how much memory you have. So you can basically feed in your schema, table config, your ingestion rate, your hot warm data. Let us say you expect 5 days of warm data, that sort of thing, and then the amount of memory that your systems have. And it's going to spit out a few segment sizes that may be good for you. And then you can also give it the number of hosts that you plan to run. Because if you increase the number of hosts, then there is less partition consumed per host. And therefore, that also affects how you want to configure these. So it's going to spit out some optimal configuration for your setup. And so we always recommend you to run that and see what it says. Run it with, I don't know, 2, 4, 6, 8, 10 hosts. And then it's going to come back and say, if you have 6 hosts, then you do this much. If you have 10 hosts, then you do this much. If you have 2 hosts, it's not going to work. So it's a dash dash, and so on. Recently, we also added auto generation of data to this. So usually what used to happen was this provisioning helper used to take an existing segment, completed segment, derive some characteristics out of it, and then give you the answers for optimal segment sizes. But recently we added auto generation of data. So you just give it a schema and you give it some cardinality information, and it's going to auto generate the data and then compute some segment sizes for you, some optimal sizes, and you can use those. You can configure this pinot.server.instance real-time alloc off heap. That is the one that allocates off heap memory for consuming segments, which is predictable, less GC when segments completes. I believe this is a default now. If not, we should probably make it a default because the heap allocation for all the other dictionaries and everything is pretty much very, very expensive. in terms of GC, because things get accumulated over time, and then when the segment completes, there is a huge GC with releasing a whole bunch of these things. Um, there is the consumer directory that you can configure. It allows you to choose a directory in which the memory map files should be present for the consuming segments. Because they are read-write, you might want to give special attention to them sometimes. For example, you could use a memory-based file system so that if there is continuously, a lot of dirty pages, they're written back to a memory-based file system, and then you don't incur disk penalty on those. And lastly, there is the number of parallel segment builds. If you have 20 partitions being consumed on a single machine, and you really don't want to have all of them, go through segment build at the same time during completion, there is an optimal number that you can set that you prefer. By default, it is all of them will happen simultaneously, and you might run into problems. You might not if you had sized your system correctly in the beginning. And then there is the recommendation engine that we have added recently. It's called it's controller. It's a controller command. So you can go to the controller and go to the recommender API table/recommender. You give it some input, and then it's going to come back and say, here are the possible configurations that you can use for your table, possible optimal configurations you can use for your table, and I believe it also runs the provisioning helper. I'm not 100% sure at this time. Okay. For batch offline tables, is there an equivalent to provisioning helper?
We do have another question too. So I was just going to wait until the Q&A. Do you want to finish up and then it's up to you?
Okay.
You can ask.
Okay. Why don't we wait until the
Q&A in the meantime? Okay.
So in case your system is undersized, what are the indications, right? And typically you won't face this. You probably, you put a few servers, you have a few partitions, and things just run out of the box. But in case you're undersized, in case you're choked up somewhere, you find SLA is going bad, what may you observe? Well, one of the things that you'll observe is server runs out of heap memory, and if it runs out of heap memory, you want to ask, well, you could increase your XMX. That will help. On the other side, you could also see if this is happening during segment completion. If so, you can tune the parallel number of segments to be completed. Or if you have too many inverted indices because they're always on heap, or if you have too many stream partitions being consumed in a single server, or too many segments committing at the same time, or a high QPS, then you basically, for all this, the only thing you can do is to add more replicas or more servers so that the partitions get distributed across them. The ingestion burst may hurt query performance. So if you have a huge burst of rows coming in, that can then the server is then busy too busy to serve queries. So one tuning factor we have there is if it happens during restart, then you can say, well, wait until some period of time before you go ahead and serve queries, and that helps. That has helped us in LinkedIn. We are also trying to add a smarter way of recognizing when we have reached a reasonable limit to start query performance. That is work in progress. But this is the setup that you can do today. So real-time consumption catch-up wait, and you can set it to, I don't know, 2 minutes, 3 minutes, whatever you think is useful after you restart, so that it can give you the right time to start serving queries. You can throttle ingestion into the topic if that is possible. Unfortunately, aside restart, we don't have any other way to control ingestion bursts. If it comes in, we do consume it. We did try out some experiments on rate limiting. That's still experimentation. So we don't have anything concrete on that today. More indications: you have high query latency. Check the bottleneck. Are you paging? Paging is very common if you have a lot of consuming segments. And what is the ratio of hot to warm memory to the total memory you have? If that is high, then you're going to be paging, and then you've got to do something else. For all of these, typically adding more servers helps. So if you started off with more number of servers, you're unlikely to see any of these problems. You can also consider using SSD for both completed and consuming segments, or memory-based file system. Like I said, those can reduce paging and also improve query latency. Of course, adding more hosts. You can move completed segments to another tenant. We have that available, and we use that in our multi-tenant environment so that we can isolate all the consuming segments to one tenant, and then the completed segments on another tenant to be characterized exactly like the offline segments. You can add an offline pipeline to make it a hybrid table, and that will basically limit the number of hits on the real-time machines, and therefore leave enough room for them to consume rows. You can use an optimal segment size as recommended by the provision helper, and you can add appropriate indices, but adding an index also takes away memory, so it's a double-edged sword there. If rows are showing up late, it's never happened, so let me say that. Maybe segment completion is taking too long. You might want to look into what's going on there, look up the logs in the controller, and it might show you something. One likely case is that we have a segment store that we're trying to upload to, and that's taking a long time. And because there's a pause during completion, the rows are taking a while to show up. Okay. Some of the futures. We want to reduce consumption during real-time segment completion. We want to continuously optimize the segment size. So right now, you give it a segment size, and we learn to get to the right segment size. But once we do that, we really want to optimize it to the tune to your table, so that bigger segment size or smaller segment size suits it better. We want to do that. We want to rate control and budget on ingestion, so that if extra ingestion comes in, we just rate limit that in terms of consumption. And we want the option to use peer download only and no uploading of real-time segments. That can get better in terms of segment completion. Can take less time, but it has a risk, of course. You don't have a stable storage for the segment. Continuing ingestion while completing the segment, and off-heap inverted indexes. These are all in our wish list, but we haven't yet gotten around to doing many of those. And multi-tenant real-time is a big open thing. It's really hard, especially while serving. If single tenant had so many variables that I described, imagine how it will be if you have multiple tables all consuming on one machine. That can be really tricky. So some of the key problems there are: how do you rebalance across tables, and what about capacity and headroom estimation? And then can we have a per table quota for ingestion? These are some of the links in our document in docs. Pinot docs in Apache. This one is a blog that I wrote a while ago, auto tuning Pinot real-time consumption. So it's a good read if you followed this talk. We're always looking for contribution, and thank you so much. I think I exceeded my time a little bit.
Oh, it's okay. Better the content. This was such a well put together presentation. I'm really impressed.
Thanks.
I was like, it's a lot of content, and it's very dense. It's really, really good. So thank you so much for taking the time and putting this all together. Because I'm like,
absolutely.
I'm like thinking in my head, I was like, there's definitely people who are going to be rewinding through this and like holding still on the slides. If you do have those URLs for the slides, you can send them over to me, the ones that are just hyperlinked, and I'll add them to the description of the video on YouTube so people can access them easily. So if anybody has any other questions for Subbu, we're going to go to Q&A now. So please ask now in the chat, but I'll start feeding in the questions. So Sadim asked, is the query latency going to suffer over time if my retention period is large and no segment increases over time?
Number of segments increase over time.
Number of segments.
Yeah, I mean, if you're going to query, I mean, that's what I would think. If you're going to query 30 days and 45 days and 60 days and over time, and yeah, you're going to scan more data to get your results, and I would imagine it's going to suffer, but you can add more servers. If you have the same number of servers, it's probably going to increase. But if you add more servers, then it's going to be distributed, and then you're going to be good.
Okay. Ken asked, for batch offline tables, is there an equivalent of real-time provisioning helper? If not, then wanted to circle back on the question of how best to estimate memory needs with replication.
Yeah, good question. So for offline tables, the closest we have is the recommender link that I gave. It's fairly easy to do the offline estimate because for memory purposes, it's the segment size. So if you have your segment sizes, or if you have your rough data size, that is your memory used for offline. And so you can then choose a ratio of that with your available memory to decide how much paging you want to take and how much latency you're willing to tolerate.
Awesome. Okay, and then Elon asks, what is the best way to manage controller responsiveness during bursts of ingestion due to uploading many offline segments on the controller?
Okay, the talk was more real-time ingestion, but yes, if you have multiple ingestion on the controller, many things can play a part there. Your deep storage could be slow, because of which controller is holding up threads and is not able to release them because those threads are slow there, so writing to deep store. Or if you have, I mean, it's unlikely that you have so many segments that the controllers are overwhelmed. But you could add, if your deep store is fast enough, you could add more controllers. We do scale up to 20 plus controllers per cluster. If you did have more than 20 controllers, just something else wrong with your cluster, you probably need to split it.
I just want to mention too, before we go to the next question, we do have another presentation coming with Jackie on optimizing query performance, which index to use, and filter optimizing and segment pruning. So that's coming up right after the Q&A. So please hang on if you guys are still here. I know we're doing the Q&A now. Ken's other question, also, how best to size the JVM broker memory needed for consuming groups of from servers to construct the final result?
Yeah, the broker memory sort of depends on your queries. If you're doing distinct queries, then you do get the exact results streaming from the servers to the broker, and there's huge memory to be tackled there. But if you're doing aggregations, you're probably okay. So we don't have a formula on that. Sorry. Maybe cool. Jackie can have something under his sleeve. So
yeah, we'll bring him back in. He can add to it if he wants to beforehand. And is there a way to stagger throttle segment completion to avoid a thundering herd?
Yes, so that is the configuration that I gave you. So you can limit the number of segment completes per host. And there is not a way by which across hosts you can stop that because all of these go to the same controller, to the lead controller to do the completion. But the controller part of it is really small. The main thing is actually building the segment. And so if you can control that on a per host basis, you're good. And this worked for us.
Nice. Awesome. We do have some people who just commented, great presentation. That was pretty slick. That's a fun comment. Awesome. Yeah, Subbu, this was really, really good. Thank you so much for taking the time. You can definitely tell that you took a lot of time and thought on putting together this presentation. And I also appreciated the humor because I was laughing backstage when you were making jokes. So that was really good.
Yeah, thanks, Corinne, for organizing it.
Yeah, no, this is awesome. Oh, we do have another question that just came in. So we'll ask this question. If there's any other questions, we can either ask it in the Slack or we can do it after Jackie's presentation. Oh, wait a minute. Same question. Let's see. How does the real-time upsert on older data affects the ingestion performance?
I think it does affect. I don't have a measure of it at this time. Sorry.
Okay, cool. All right, yeah, it's also maybe something Jackie can answer. If Jackie comes on and he wants to tackle a couple of the questions beforehand, then it's good too. Okay. Subbu, thank you so much. This was cool. Really,
thank
really
you
awesome.
all. Thank you all.
We definitely, I know this is probably a lot for you to prepare for because the content was definitely awesome and very well put together. But I definitely think that you'd be highly valuable doing presentations again in the future.
Sure thing.
Yeah. The community. All right, so I'm going to put you backstage and I'm going to bring out our next speaker, Jackie Jiang. He's a founding engineer at StarTree, Apache Pinot PPMC and committer. So his little background is that he is a founding engineer at StarTree, which I just said. Before that, he worked at LinkedIn Pinot team for 4.5 years and became the PMC and one of the top committers for Apache Pinot. Jackie's goal is to make Apache Pinot the fastest online analytics platform on the market, which I love so much. Hi, Jackie.
Hi, Corinne.
Hi. So yeah, if you have any feedback on the questions that were asked, you can feel free to add to it, or we can just jump to the presentation. You want to just get right into the meat, or?
Yeah, I think I can add something to the last question about the real-time observe. So for observe, because it requires all the segments for a partition to be on the same server. So, and also like the observed metadata is maintained in memory. So basically, I don't think there's like actual overhead to observe on older data versus new data. So yeah, basically that's the question. So there's no obvious overhead around that.
Awesome. We do have a final comment. Just segment flush periods. What is optimal? Is this still a question? But we might be just going into Q&A forever. If you want, we can also tackle this at the end of your Q&A too.
Yeah, and also I think, this one you can use the tool Subbu provided. So for different use case, like you might want to configure different flash periods based on your segment size. And basically the tool should give you a good recommendation.
Cool. We will, for those viewing, we will be doing a Q&A afterwards, and we can also bring Subbu back out if you have more questions for Subbu before we end everything. So we will be doing a Q&A afterwards. We'll bring him back out if he's ready for it. Okay, Jackie, I'll let you take it away when you're ready.
Cool.
Cool.
Okay, thanks,
I'll
Jiang.
see you at the Q&A shortly.
Sure. So yeah, feel free to interrupt if there are any questions. And then
I can interrupt if it makes sense, but we can also save it for the Q&A at the end.
Cool. And okay, so thanks Subbu to give like a really good presentation on like how to optimize the real-time performance. And then Subbu's talk is more about from the data ingestion and the data management perspective. So my talk will mainly talking about how to optimize the query performance using the correct index and also some like special techniques to like prune segments. So first, Subbu already gave a pretty decent overview of the Pinot architecture. So here I will give a brief overview on the components that are used to execute the query. So the components involved here are brokers, servers, and segments. So first, when broker receives the query, it calculates a routing table and then route the query to the servers. And server gets the query, it executes the query on all the segments, not necessarily all the segments, on the segments hit by this query. And then after getting the segment responses, it merges the segment responses, and then the broker gathers the responses back from server. Then on broker side, it merges the server responses, then it returns the final response to the client. So this is the life cycle of Pinot server query. So let's go over each component in this graph. So first component is broker. So broker maintains the mapping from server to segments hosted by each server. And then when receiving a query, broker is responsible for calculate the routing table. Basically, the routing table is like where all the segments hit by this query locate and then which server to route the query to. And then broker scatters the query to the servers hosting the segments. And then the last step is after a server responded, so broker gathers all the server responses and then merge them and then return the final response. Okay, so let's take a look at the server. So server, first, it hosts the segments. And then when it receives the query from the broker, it executes the query on the segments. And then it merges the segment responses and then send the server response back to the broker. Okay, so last component is segment. So if we zoom into the segment, we will see, so it wraps a block of records. And segment is the smallest query execution unit within Pinot. And within segment, it contains the column indexes. So Pinot stores all the data in columnar fashion. So within segment, you will see indexes. Basically, it's not the index is not for each row, but for each column. Okay, now let's see how a query is executed on a segment. So, for example, let's take a look at this very simple query. Like if we want to do a sum on column A, where column 2 equals 1, 2, 3. So to solve this query, there are two phases. First, we need to do the filtering. Basically, we want to find all the records that match the predicate column 2 equals 1, 2, 3. And then after we get all these records, then we want to do the aggregation, where we read the column 1 values for all the matching records and then aggregate. So then let's take a look how to optimize the performance for this query. So from query execution, so broker first get the query, then route the query to the server, then server execute the query on the segments. So from performance optimization perspective, I want to go bottom up. So let's first take a look at how we can optimize the query performance on segment, then server, then broker. So first, let's take a look how to optimize the query performance on segment. So we'll still use this query as an example. And then in order to solve this filter, if we don't have any special index on this column, in order to solve this filter, we need to scan all the values for column 2 to find out all the matching records. Basically, we need to do a full column scan and then find all the values that I want, find all the records that has column 2 value 1, 2, 3. So this can take majority of the query time because basically we need to scan every individual values for this column, and especially when the selectivity is high. What selectivity is high mean is like there are only very few matching records. The reason being, like if there are very few matching records, then the aggregation phase is will be like very cheap because we don't need to process much data. Then the majority of query time will goes to the filtering phase. So here we want to optimize on this filtering. So first index I want to introduce here is inverted index. So inverted index maintains the mapping from value to the records that match the value. And then the records are stored as a bitmap. The matching record IDs to be more specific. So here let's take a look at an example. For example, I have a tape. I have the segment that has the following records. So as we can see, like for record 0, column 1 has value 5, and then record 1 has value 10, and so on. So if we convert this into an inverted index, it will look like this. So basically, it is a map from the column value to the record ID for this value. So as we can see here, so for column 1, value 5, there are 2 matching record IDs, 0 and 4. And for column 1, value 10, there are also 2 matching record IDs, 1 and 3, and so on. So with this inverted index, we can solve this kind of filters. First, let's see, like if we want to solve the filter column 1 equals 5, we can directly look up this inverted index and find, okay, there are 2 records matching this value. Similarly, for column 1 equals 10 and 1, 2, 3, it can be easily solved with just one value lookup. And then if the query has, for example, a filter column 1 equals 1, then after look up the map, we found, okay, there's no matching value. Then we know, okay, there's no matching record. Then basically, we know there's no like we can skip the aggregation phase because there's no records matching this filter. Okay, so inverted index is the most commonly used index to optimize the filtering performance. And it can be used to solve these predicates. So as we already covered, it can be used to solve the equal predicate. For example, column 1 equals 1. It can also be used to solve the not equals. So to solve this not equals predicate, basically, we can first get the bitmap for the equal predicate. Then we can basically reverse the bitmap. Basically, like we can I would say, subtract this bitmap from the whole document range. Then we will get the result for this not equal predicate. So similarly, we can solve the in predicate by union the bitmap for all the values in the in clause. For example, here, column 1 in 1, 2, 3, I can get the bitmap for value 1, value 2, and value 3, and then do a union on top of it. Similarly, for not in, I can first do a union on these values and then reverse this bitmap from the whole doc range. But let's take a look at another type of predicate, range predicate. So inverted index becomes less efficient for range predicate. For example, I want to solve a filter column 1 larger than 5. The reason being, in order to solve this, I need to collect all the possible values for column 1, and then I want to union all the bitmaps. But then there might be too many matching values. For example, I have value 6, 7, 8, blah, blah, blah. And then so in order to solve it with inverted index, I might need to do a union on, let's see, a lot of bitmaps. So like merging so many bitmaps can be very costly. So to solve this problem, I want to introduce another index called range index. So range index is designed to optimize the range predicate. It maintains the mapping from value range to records matching the range. So as we can see, it is quite similar to the inverted index. The difference is the key for this mapping is the value range instead of each individual values. So let's take another example. So for example, here's my segment data. And then to convert it into a range index, it will be something like this. So the key is actually a value range. So here we can see like the first entry is for column 1 of value range 0 to 10. And then from 0 to 10, we found 2 matching record 0 and 4. So the value is 3 and 5 for these 2 records. And then similarly, for value range 10 to 20, there are another 2 matching records, 1, 3. And then for value larger than 20, then there's only 1 matching record, 2. So let's see to solve. So using range index, we can easily solve these queries, these filters. Like for example, column 1 smaller than 10, then we know, okay, we look up this range index mapping and then found, okay, only range 0 to 10 match this filter. Then we found, okay, record ID 0 and 4. And then column 1 smaller than 20, similarly, we found column 1 of range 0 to 10 and 10 to 20 match this filter. So we do a union on this 2 record ID set and then get the final result 0, 1, 3, 4. And then column 1 larger or equal to 20, we found, okay, it matches the entry 20 to 30. Then we found, okay, there's only 1 matching record ID, which is record 2. So far we can see all this filter match the value range boundary. So how about this filter? Column 1 smaller than 15. So we found, okay, there's no value range that has 15 as the boundary. So how do I solve this query? So So basically, this case is when value is not at the range boundary. To solve this query, we look up this. Similarly, we look up this mapping, and then we found value range 0 and 10, 0 to 10 is always falling into this predicate range, which is larger than 15. So we know record 0 and 4 always match. And then value range 10 to 20 might match this range predicate, which contains records 1 and 3. And then 20 to 30 won't match because this whole value range is larger than 50. So in order to get the final result, we can scan the records within 10 to 20 range, which are records 1 to 3. And then we found record 3 matches, and then record 1 doesn't match. Then we can add this actual record to the always match record IDs, and then get the final match records 0, 3, and 4. So to summarize for range index can be used to optimize the range predicate. And then when the range predicate value is at the range boundary of the range index, there's no scan required. When the range predicate value is not at the range boundary of the range index, we need to scan the records for one value range. But we don't need to do a full column scan. So for example, if we have, by default, we have 20 value ranges. So in this case, we only need to scan 5% of the data in average. Okay, so far we have covered the range index. Let's take a look at another very powerful index called sorted index. So sorted index is very powerful, and it can be used to solve all the predicates mentioned above, equal, not equal, in, not in, and also range predicate. But it requires the values to be pre-sorted within the segment. So it cannot be applied to all the columns. Since it requires the column values to be sorted, in most cases, it can only be applied to one column. And usually, we would like to apply it to the primary key column. So primary key column is not a concept in Pinot, but for other databases, basically you can think of it as like a column where you most likely put a filter on. So for example, we have this data set. And then to convert this to sorted in, as we can see here, so the column 1 values are already sorted in this segment. So to convert this into a sorted index, we keep a mapping from record value to the column value, from the column value to the record ID range. Because the column is already sorted, so record ID is always a range. And then basically this range are also sorted. So here, let's take a look at how to use sorted index to solve the query. So for equals, not equals, in, not in, sorted index, basically we can use it as inverted index because it also maintains a mapping from each individual column value to the records. And then we can easily convert this record range into a bitmap. For range predicate, because the values are already sorted, we can perform a binary search on the values, then get the matching records IDs. For example, we want to solve this predicate, column 1 larger than 3. So we look up this sorted index entries, and then we found, okay, the first matching value is 5. So so basically the record ID will be everything after column value 5. So we found column value 5 has record range from 2 to 2. So we want to pick all the records that has ID larger than 2. And then basically in this use case, it is 2 to 4. So one thing I want to mention here is sorted index in general has better performance than inverted index and random index because of the data locality. Here, the selected records are usually like stick together. So when we scan for the aggregation phase, we get better performance. So far we have covered the most commonly used indexes type. We also have other indexes to optimize for some special predicates. So I'll just list them here. So, but I won't go deeper into it because for time's reason. So first we have this non-value vector index. Essentially, it's inverted index on a column to store either the column has non-value or not non-value. So it's used to solve the is null and is not null predicate. Then we have the Lucene text index, which can be used to solve the text match predicate. We have Lucene FST index for the regex like regex expression, regular expression like predicate. Then we have the JSON index for JSON match and H3 index for the geodistance range predicate. So several of them are already covered in the previous meetups. So you might be able to look it up in our YouTube channel. So far we have covered all the indexes to optimize the filter. Then let's take a look at the next phase, the aggregation phase, how to optimize that. So if there's no filter, or the filter has very low selectivity, meaning most records match the filter, then the aggregation phase could be the bottleneck because it needs to scan values from lots of records. So here we have a special index called StarTree. So StarTree index basically pre-aggregates the records. And then it can significantly reduce the values to be scanned during aggregation. So StarTree index is quite complicated. I won't cover the detail of it in this talk, but it's so powerful, so we named the company after that. So if you are interested, please read more about StarTree in this link. So basically, we have a blog describing the use cases and then the layout of the StarTree, and then it is also available in the Pinot doc. Okay, so far we have covered all the techniques we have to optimize the query performance on a given segment. Now let's take a look at how to optimize the query performance on broker and server. So with all the indexes I already described in the segment, we can achieve very good performance executing query on the segments. But what if we want to do one step further? So for some super large use cases, for example, like if a table has petabyte of data and then let's say 100K segments, or some use case might have super high throughput requirement, for example, like more than 10K QPS. We want to further optimize the query performance to meet the SLA and then also probably reduce the cost of the hardware. So here on broker and server, we can use some techniques to reduce the segments to be processed for each query. So first, let's look at the query optimization we have on server, the Bloom filter. So let's still use the same example. So to solve this predicate column 2 equals 1, 2, 3, we can configure a Bloom filter on column 2 to quickly filter out segments that do not contain value 1, 2, 3. So Bloom filter is very efficient, usually on high cardinality columns, like whose value don't repeat a lot among segments. For example, transaction ID is a great example for applying Bloom filter. If we want to find the records of a given transaction, the query will be like select star from table where transaction ID equals like probably a UUID or something. Then basically a transaction ID won't repeat a lot among segments. So this transaction ID might only exist in 1 or 2 segments. So with bloom filter, for example, if the false positive rate is 3%, that's a common false positive probability, then here, in regular case, around 95% segments will be pruned out. So we only need to process 5% of the segments. So bloom filters, because we need some actual storage for bloom filter, so bloom filter are stored on server side along with the segments. So next, let's take a look at the query performance optimization techniques on the broker, partitioning. So let's use the same example. So we can partition the data on this column 2, so that each segment only contains column 2 values from the same partition. And then with the data partitioned in this way, column 2 equals 1, 2, 3 will only hit one partition. Will only hit the partition that contains the value 1, 2, 3. So in this case, we only need to pick the segments from this partition in order to solve this query, because we know the segments from other partitions can never contain value 1, 2, 3. So partition info is stored within the zookeeper along with the segment ZK metadata. So it is accessible to all the brokers. Broker can prune the segments based on the partition info and only route the query to the matching segments. So it doesn't even need to route the query if the segments is not in the correct partition. So let's take a look at different partitioning mechanism in Pinot. So first, there's time partitioning. So by nature, time series data is usually partitioned by time. For example, if we push segment each day, then the segments will be the data will be partitioned on each day. So for example, some queries like select something where event time between August 1st to August 5th. So this is a very common query. And also for hybrid table integration of offline part and real-time part, there's always there's always a time filter attached to the query. So the time partitioning can also help with that use case. So for this query, segments for all other dates are pruned because they won't match this time predicate. Another type of partitioning is called value partitioning. So Pinot also supports partitioning based on the value of the column. So one most commonly used partition function is murmur2. So murmur2 is the default partition function in Kafka. So by using partition function murmur2, we can automatically get the partitioning info aligned with the Kafka consumer, and then real-time then the real-time segment will get this partitioning. So for example, one example for the value partitioning is to solve predicate member ID equals some value. So if we partition on member ID, then we only need to pick the segments from this partition which contain the member ID value 1, 2, 3, 4, 5, 6, 7, and then only process these segments. So let's say if we have 20 partitions, then only the segments from one partition need to be processed, meaning 5% of the data. Then another 95% of data are pruned. Okay, so to further optimize the query performance for partition data, so we can configure the Pinot to assign the segments for the same partition to the same server. So by doing this, we can reduce the fan out from broker to the servers. Because let's say a query only hit one partition, I only need to query the segments for that single partition. then I only need to query one single server. So this topic is already covered in a previous meetup segment assignment. So feel free to check it out in our YouTube channel. So far we have covered all the techniques to optimize the query performance. We do have some indicators from the query response. So if you send a query in the Pinot query console, you will get a response similar to this. So as we can see in this query response, on the top we get the query response stats, including the time used and some other metadata. And then if you choose to show the JSON response, you will see all this metadata in the JSON. So these query response stats are very good indicators for opportunities of query optimization. I'll go over some of the important indicators here. So first, there's a stat called number entries scanned in filter. So it counts the number of values scanned in the filtering phase to solve the query. So if we found this value very large, then probably we want to add some index in order to reduce the scan during the filtering phase. For example, the inverted index and range index. And there's another, so the name is quite similar. It's called number entry scan post filter. So it marks the number of values scanned after the filtering phase. So for example, the values scanned in selection, aggregation. So in this case, if we found this value very large, then we might want to add StarTree index and do some pre-aggregation on the records to reduce the value scan. Another set of indicators, number segments queried, number segments processed, and number segments matched. What does these three values mean? So first, the number segments queried are the number of segments queried by the broker. So enable partitioning can reduce this value. And the number segments processed means, so basically number of segments queried are the number of segments the number of segments server get from broker to process, and the number of segments processed are the actual number of segments processed by the server after server prunes the segments. So adding Bloom filter can reduce this value. Then the last one is number of segments matched. So it is the actual number of segments that have records actually matching the filter. So if this value is much smaller than the number of segments processed, it means we still have some opportunity to optimize the server segment pruning to prune more segments without processing them. So in the end, we have another two stats about servers. So the first one is number of servers queried. So it is the number of servers queried by the broker for this query. So enable partitioning, and also the partition-based segment assignment can reduce this value. Basically, this is the fan out of the query. Then another one is number of servers responded. So this is the number of servers responded, and if this value does not match the number of servers queries, it means some servers didn't respond. For example, like some of the server timed out, and then the result is not complete. So user can choose to retry the query or accept a partial response based on the use case. Yeah, so that's all about my my presentation. And then I didn't cover how to configure the index, so you can check that out in our Pinot document. Okay, so let's do
Awesome.
a Q&A.
Jackie, yeah, I can't believe how often you do this. This is crazy. Like, this is so much information, and like, I'm really impressed. Week after week, you're here doing this. So it's awesome. It means a lot that you are taking the time to like help people figure out all the stuff that you've been working on.
Yeah,
I'll bring. What were you going to say?
Sorry.
No, you say.
No, I'm saying like since everyone who work on this project and build so many awesome features, so I have something to talk about.
That's great. All right, so I'll bring Subbu back out and I'll start bringing in some of the questions because there has been some conversations. I'll bring them back in. So hi, Subbu, welcome back. Okay, so I'll start here with Sadim. If column type is not int or long, if it's string, then will query performance not improve as much?
I mean, is this a question about, I mean, in general, string has, yes, slightly worse performance compared to int and long, but if the values are dictionary encoded, then usually the overhead is just when you look up the dictionary. After that, we use dictionary ID. So the performance would be the same. So yeah, I think that's the answer. So the short answer is, as long as the values are dictionary encoded, you won't see much worse performance.
Subbu, did you want to add to that? I see you nodding. Oh, your volume is, I think your headphones, your sound is off.
Okay. So,
there we go.
So yeah, the other part is if you use no dictionary, if your cardinality is generally small, then yes, that you can use dictionary and that's fine. But if your cardinality is huge and you're not going to search on it, then you can use no dictionary as well. And that way, then we only pull out the rows that that are finally filtered out in the query.
Cool. Okay. How performant the inverted index when the column is cardinality is high or unique? And also Mayank chimed in here, so I'm just going to show his response. Setting inverted index on a high cardinality column typically helps as it can help prune out larger numbers of records from scanning. Do you guys want to add anything to that?
Nope, he said it.
Okay.
Yeah.
All right.
The only thing you might want to consider is the index size, but performance is not the problem in this case. It's mostly about index size because for each value entry, there's a bitmap. But we use routing bitmap, which is fairly good compressed. So in most cases, I would say you don't need to worry about that.
Okay, so here's another question with a little bit of a conversation. So I'm just going to put it all on the screen over here. So for sorted index, can we use multiple columns? Ken responded, I think only one column for sorted since the entire segment has to be sorted by that field. And I assume not a multi-value field. And then Elon, to clarify, said, I meant something like a composite key. Is that possible? Example, timestamp version, or is this not done for performance reasons?
Jackie, you want to take that?
Composite key. I'm trying to understand this. So are you saying sort on a composite key?
Elon could probably clarify. We can ask him to clarify. We can jump to the next question and have him elaborate.
Yeah, but I can add a little bit on the sorted column. So sorted column is automatically figured out by Pinot, so you don't need to explicitly configure it. So when Pinot generates a segment, it will automatically figure out whether all the values for this column is sorted. And then if so, it will automatically generate sorted index for this column. So for an example, let's see if you have some column that only have one single value, then it is always sorted. So in that case, you can have multiple sorted columns. So basically, Pinot will automatically figure out which column is sorted and then apply sorted index. So for this composite key, yeah, I think I might need to understand the question.
I think he's asking if there is, if Pinot supports the first order, second order, third order sorting using composite keys. And the answer is right now we don't. But I've seen discussions about this. So who knows when it's going to come by. And going back to the sorted column, what Jackie said was correct about the offline segments. For the real time, you can specify, and we encourage you to specify one sorted column because the rows don't arrive in a sorted order in general. So we ask that you do specify one column that you want to sort on, which is your primary key that you're going to search on most of the time, and then we sort on that basis while building the segment.
Yeah, thanks Subbu for adding that. Yeah, so actually sorted index need to be configured explicitly for real-time segment, and then during consumption it won't be sorted. So we will use inverted index, and after the consumption is done, and when the segment is committed, we reorder the records based on the sorted column. So the records are sorted on that column.
Got it. Okay, can applying too many indexes or providing too many columns in StarTree lead to an out-of-memory error? How is the memory usage handled?
This is a good question. So based on this question, I know you already have a pretty good understanding on the StarTree. So the short answer is yes. If we add, not applying too many indexes, but if you add too many dimensions to the StarTree, and then all these dimensions, for example, are all with high cardinality, and then there's not much records with like common dimension combinations, then first of all, there are not much pre-aggregation happening there. And second, you might run out of memory, and basically there we are trying to pre-cube everything on a huge number of combinations. And then even if it works, I doubt if it can give good performance. And by default, if you don't explicitly configure the StarTree, we will only pick the dimensions that's not with too high cardinality to prevent it running out of memory.
Okay, another question. Is creating the StarTree index on hard cardinality column, Tumble unique, cause any issues, like more creation segment creation time or anything else?
Yeah, I think I just mentioned the case where creating a StarTree on a very high cardinality column. But actually, so if you have a high cardinality column, and then you want to filter on that, usually inverted index is good enough because you already get pretty good selectivity. And then you won't get a lot of records that need to be pre-aggregated.
Elon said, great presentation. This is amazing. Okay. Another question. Can multiple indexing techniques be applied on one column? How does the cardinality of column affect indexing and querying?
The answer is yes. So you can apply all these indexes to the same column. And then based on the predicate, Pinot will choose the most efficient index to solve the query. And how does the cardinality of the column affect indexing and query? So cardinality of the column won't, based on index type, it might or might not affect the query performance and the index size. For example, inverted index, higher cardinality means a larger index size usually, but then it won't affect query performance much. For range index, cardinality doesn't matter because it stores the value range. So the answer is like depending on the type of index.
So we might have to put some kind of restriction on the questions because they are flooding in. There's a lot. So I think we'll let one more question come in, and then everybody else, if you have other questions, you can ask Jackie and Subbu on the Apache Pinot Slack. They are very active there. So you can also, if you love the presentation, please give it a thumbs up on YouTube, and also you can thank them publicly on Twitter or in the Slack or wherever you'd like to. Okay. I'm not even going to read this. Is this good to use in a query or no?
It's good to use.
Regex expression.
I mean, I mean, it could be an expensive query, but still, like depending on your use case, I wouldn't see like regex expression will cause problem. Like especially if you have the losing FST index configured. So for if without any index regex expression, so basically you need to scan the values for that column and then match that regex value by value. But we process that in the end. So if you have inverted index on other columns in the filter, then you can still get pretty good performance. So I wouldn't say it's like don't use it. Like we provide it for you to use, right? Basically.
Okay. Can offline segments benefit from manually partitioning them similar to real time?
Offline segment.
We do have partitioning, allowed for both. So in fact, you can partition, you can set your partition function and then partition the offline segments so that the pruning is done at the broker level, and only those segments that fall into the partition are considered for query. And we use that in multiple use cases at LinkedIn.
Cool. This might be somewhat of a specific question here. What is the recommended indexes for, I'm not going to read this because it just would sound ridiculous if I tried to read it.
Data. So if you have...
Depends whose recommendations you like. Jackie's recommendation or my recommendation? Just kidding.
No, I would be interested in hearing the opposing views here. That's not a bad idea for one of the future meetups, is we tackle some problems live on air and see how the responses to it. That could be fun.
Yeah. So actually, I have this example in the time pruning part. So usually if you do like daily segment push and then each day the segment contains the same event time, then the filter can already be handled by the time pruning. So you will only hit the segments falling in this value range. Then after that, if you found, okay, there are too many values scanned to solve these two sum aggregations, then you might want to consider adding StarTree.
By the way, Subbu, if you have anything to add to it, please just add. If I'm jumping too quickly between questions,
I want to listen to Subbu's recommendation.
Can StarTree perform range filtering without range index or sorted index?
Can StarTree perform range filtering? Sorry, I'm not 100% sure, but conceptually it can, but the reason why I'm not 100% sure is range filtering. So basically in StarTree, each value node it's structured similar to inverted index. And then actually I think it can perform range filtering. So without range index and sorted index. So StarTree index is a special index, so it wraps other type of index inside. So basically, you can think of StarTree index something like combining inverted index and sorted index within, because we reorder the data within StarTree. So you don't need extra index in order to use StarTree index.
Okay, we're getting towards the end. There's, I think, 2 more left. So these are good questions. So I'm just rolling with it. According to the docs, the raw value forward index is not doing any particular index. That means no index. Can you please talk about it? What exactly does it do?
Sure. Subbu, do you want to?
Yeah, sure. This is what I had mentioned a while ago about no dictionary columns. It's also called raw index, which means that you're not going to have filters on those columns, and therefore we don't have to look it up during selection. So then we can come, or you're going to only project those columns at some point, and then but the selection of rows has been done by other filters that you have. So yes, that means basically the raw values are stored in order of rows.
Okay, cool. Thank you, Jackie and Subbu. Oh my God, there's more questions coming in. I don't know when to cut this off. So if this is too much, we'll just.
Yeah, I need to have for my next meeting soon. So.
Okay. So we'll take this one and then we'll take Elon's kind of clarifying question and then we'll have to cut it off, unfortunately. Unless Jackie wants to stay on and just answer questions for the next 3 hours. This became like an optimizing query performance in Pinot Q&A. I think the Q&A is like almost longer than the presentation. Does the primary time column format have impact on the query latency? I mean, if it is a timestamp as a long value, then will it be better, or can we use a date format with DDMMYYY format?
The time. So what matters more is the granularity of the time. So for example, if your time is stored in daily granularity, then basically you get much lower cardinality for the time column. If you store in millisecond, then the cardinality could be very high within each segment. So it doesn't matter on the actual format, but the granularity of the time.
Okay, yeah, I think Elon kind of addressed this too. Version for the sorted similar to Postgres composite key. Okay, and then this is the last question, so we'll just ask it because we're here. This is the final question, and then we're going to wrap up. How do the null values in a column affect the indexing on that column? That's a good question too.
How do the non-values in a column? Yeah, good question. So non-value internally, we put a default value for all the non-values. So if you want to explicitly query for non-value, you can enable the non-value vector, which is like covered in my slides. And other than that, non-values are stored as some default value, which you can configure within the schema. For example, for metric, usually we put 0 as a non-value. So it won't affect the most common aggregation, the sum. So from index generation perspective, it will just treat that as a default value.
Nice, awesome. Thank you guys so much. We're going to end this now because otherwise I think the Q&A will just keep going on forever because there are a million questions we can ask. But for those watching, the discussion does not have to end here. Feel free to join the Apache Pinot Slack and ping Jackie and Subbu, or you could just ask in the general channel or troubleshooting. And there's a bunch of people there who can probably help out too. Our community, the contributors are pretty active. So thank you guys so much for taking the time and putting together these awesome, informative presentations.
Sure.
Really.
Thanks.
Awesome. Good stuff. Really, really. And Subbu, we have to have you again when you're ready. I know it's a lot of work to do this, and we went 40 minutes over the time. So, appreciate you guys putting the energy and effort towards doing this. This really means a lot. So, all right. And until next time, guys, don't forget to comment, like, subscribe, give it a thumbs up if you like this presentation. And we'll see you next time.